Okay, so till now we have seen various features of test bench. We have gone through classes, we have gone through interfaces, we have gone through constraint randomized verification. We have gone through interprocess communication. Then we have seen the different scenarios for verifying ALU. So we have gone through the basics of system Verilog, how you can basically which can help the viewers to write a test bench. And now we can see that how those concepts are merged in this last slide. Before going on to packaging of environment, that how a module test bench at the top level module is basically written, so that the class which we have created, the verification value, the randomized values which we have, is passed to a DUT and verification is done. So in this example, you can see that there's a ALU A1 which has been already been discussed with you guys, that there was a class ALU in which you have two data, and then there is an operation select, and there are various functions which are basically returning results of multiplication, division, subtraction, and addition, and this is basically the class. So in this class, you're just making a handle of that A1, and then you have two inputs, two input handles, basically A and B, and then you have a select operator which is of 2 bits, basically for 4 different operations: addition, subtraction, multiplication, division. Then you have two results, basically which you will be able to figure out that one result is from the DUT and the other result is from the class. So that result is supposedly correct result which the specification says, and the DUT result is what the DUT produces. Now if both these results are matching, then you can say okay, the DUT is behaving correctly. If they are not matching, then you can say okay, the DUT has some issues and it need to be debugged. Okay. So after creating a handle of A1, we have just used A1.randomize, which will try to randomize based on the constraints written on over it, and see if the randomization is successful or not. If it is not successful, we will display a randomization field. Otherwise, we can proceed. And we have done is that from the class, the data A and data B are fed to A and B. And this can also be done in the same way of VIF equal to ALU underscore if as well. So in this case, this is more standard approach, where virtual interface is given a handle of an actual interface, and the signals basically passes from the actual interface to a virtual interface, and then you are basically doing an operation select, and you are passing all the inputs to the DUT through this implementation. So you can also do it through a mod ports in the interface, and this will be explained in the in the labs as well. So this DUT is basically pass all the inputs, and you are also actually calculating the result class, and that is done through a1.alu op, which was being passed initially. From this, we can refer to slide 122 for that. And if this result DUT is equal to result class, then test passes for select operator, and this is done. And then this is like one particular test scenario of test bench. Now this is basically passed through different kind of randomized values and different kind of select operator, which can be passed as runtime options, and hence the whole verification is done in this way. So that basically concludes how you can write a test bench over the for the ALU DUT, and you can write constraints, you can randomize variables, and you can see the power of verification through system Verilog. So once all this is done, we come to an important point, that how your verification environment is basically packaged and delivered to the customers. So because there are lots of scopes and resolutions need to be done in while packaging a whole test bench design. So package declaration is basically a mechanism for sharing data, parameters, tasks, functions, nets, variable across multiple modules and interfaces. So it can also happen that if in a huge SOC where there is a complete set of new verification environment, that verification environment might consist of some hierarchical verification environments as well. So it may happen that in a package you may include some verification environment, and you may not include you may want to ignore some verification functions or tasks. So that kind of packaging has to be done. So in this packaging, you have to create a new scope, and which it appears at the outermost layer of source text. Functions can also be added in this parameter in this package, where you can actually, like for example, if you want to have a display function, or you can have a scoreboarding function, that can be actually added at the top end of the of your design. And the compilation of package must precede the compilation of scope in which the package is imported. So this compilation of package, it should always precede the compilation scopes in which the package is imported. So for example, if you have my package in which parameter n equal to 16, local int value is 3, and this is the package which you want to compile for ALU. If you want to have a different package, then you just change the value of n to equal to 8 or to 4 or to 64, and in that way the same package can be basically reused for ALU of 4-bit or ALU of 16-bit, ALU of 8-bit, ALU of 32-bit, 64-bit, and whatever way you want to have. So there are two mechanisms in which you can use this package. There's a scope resolution, and then there's a import clause. So in case of scope resolution operator, you just have to use like my package : print. By this, basically, even if you haven't included this package, you can just include the function print from a separate package into your own my package 2. So in that way, the package 2 will be available to you, and the package 2 will have the print function which was actually written previously in some different packages. So hence you can have multiple packages as well, and you can have multiple separate functions with separate package, and through that you can actually correlate and coordinate between different packages. So import clause also, like import my package : star. So what this wildcard import does is that it actually takes in all the information which this package declares. So it will have all the variables, all the functions will be can be used in your design once you do this import package : star. So by this we conclude the System Verilog language constructs. What we have learned is classes, how classes can be used to generate random values. Then we have learned interfaces, features like modboards and clocking blocks, and we have seen how interfaces are integrated into the class example of an ALU. Then we have come up to inter-process communication like mailbox, semaphores, and events. Then we have come up to packaging, and I will suggest you viewers to go through the running code example. So that is actually very helpful for you to actually practically test those that test case of an ALU. So for any references, you can actually consult these sites like www.asicworld.com, www.testbase.in, dulos.com, asicguru.com. So these are very good sites to understand the basics of System Verilog and its use cases and the various constructs that System Verilog provides. The Bible of System Verilog is obviously System Verilog Language Reference Manual. That will demonstrate each and every construct that System Verilog provide for verification engineers. In case of doubt, you please drop us a mail to any of us, shubham_rai@mentor.com, and you can also drop to my colleagues Naresh Yadav, Prashant Dikshit, Suraj Gupta.